All right, this bell work may look kind of familiar, but it's a little different as well. So let's go and simplify this. Now we need to remember here that the bases are the same, so we're going to keep the base the same, x. But since we see division of the bases in the original, that tells us we will be subtracting the exponents. And the exponents have to be in this order. Take the numerator exponent here first, which is 90, and then subtract from it the denominator exponent, which is negative 41. So that comes out as 90 minus negative 41, and that's okay. And that's how you'll put it in the calculator. Remember, those are two different buttons, the minus button and the negative button. So this gives us then a new exponent, x to the power of 131. Try not to overcomplicate that because that's as far as we need to go on this type of problem. But in addition to this, you're going to be seeing other problems, just kind of as a quick review for us. Remember, if the bases are being multiplied, so let's say you got 2 to the power of 8 times 2 to the power of 9, something like this. You'll keep the bases the same, so it's still a base 2, but since we see the bases being multiplied, this one will tell us to add the exponents of 8 and then 9. Okay, so this would be like 2 to the power of 17, and on the quiz that we're going to be taking today, you will not want to actually evaluate these, okay? So you just keep it with a base and an exponent, and you're in good shape. Remember too, these types of examples, so let's use the letter base again, so something like m to the power of, I don't know, 3, and then power, even if it was a negative out here. Doesn't really matter if we see that we got parentheses, so we're going to keep the base the same, but the parentheses tell us that we're going to be multiplying those exponents of, in this case, 3 and negative 4. So yeah, this one you're multiplying the exponents, so we now have m to the power of 3 times negative 4, that'd be negative 12. And yeah, the last thing I'd do on this one is just make it a fraction, so that'd be 1 over m to the power of positive 12, because we want positive exponents, okay? All right, and the last thing I'll mention on this is, remember, if you have bases that are negative, so something like, I don't know, negative 4, like this, maybe it's to the power of 5, let's see. Maybe it's being multiplied by another base, negative 4, but that has an exponent of 6. So the same rule still applies. We see that we're multiplying the bases here. So we know we're going to be adding the exponents. It's just, you're going to want to keep your base, negative 4, in parentheses, at least for full credit anyways. Okay, then you take your two exponents, 5 and 6, and you'll still add those, but again, you're going to keep your answer, your simplified form here, your base that's negative, in parentheses. That'd be negative 4 to the power of 11, something like this, okay? So that's a nice quick review of all the stuff that we've been doing in this unit. Here's our two objectives. I can write any number, big or small, in scientific notation, and then I can change scientific notation to a regular number if needed. So we'll go over these two objectives, but first copy these down, take 30 seconds, and we'll start. All right, so scientific notation may be kind of a new thing for us, but it's just a different way to write numbers. So it's a little bit more sciencey, I guess. Generally speaking, they use this only for extraordinarily large or extraordinarily small numbers, but it doesn't really matter in terms of math because we can write any number in scientific notation. So what we see here at the top is just kind of a really nerdy way to define scientific notation, and I assume you could read that several times. I couldn't memorize that, but it's really boring anyways. In normal language, it's just kind of like this. So what you're going to see is kind of a decimal kind of thing going on right here. Now you'll notice for formal scientific notation is you'll have only one number in the ones place value. You'll never have anything in the tens or the hundreds or beyond that, okay? You'll only have a number in the ones place value, and it cannot be 0. That's it. Now the decimals here, tenths, hundredths, thousandths, and so forth, it doesn't really matter how many of these you have. You just have as many as you need or want. And up here it talks about like order of magnitude. Yeah, it just depends on however many values are significant. So if you're dealing with something large, you may not even need some of these decimal place values. It just depends, okay? So I guess that's more of a significant figure thing. Now you'll see that it's always multiplied by base 10, which is good. Base 10 is good for us because that's how our number system works. For example, if you look at place values, okay, so let's look at these first three, we'll look at the first six here, okay. So you got ones place value, tens, hundreds, thousands, 10,000s, and then 100,000s. But if you look closer here, the ones place value is really just 10 to the power of 0. The tens place value is 10 to the power of 1. The hundreds place value is just 10 to the power of 2, and you can see the pattern that's going on here. Thousands would be 10 to the power of 3, 10,000s, 10 to the power of 4, and then the last one we'll look at is 10 to the power of 5. Of course, you can go into the millions because this pattern just continues to the left here pretty much forever. So this is our number system, and it is base 10. So you'll see base 10, and the reason that is because our exponents, any exponent will do. You can have negative exponents and positive exponents. Later on, although not in this class, you may see some decimal or fractional exponents, but we don't care about that for now. But the exponent in scientific notation, if we were changing this into standard form, which is just a regular number, then the exponent tells us not only how many times to move the decimal, but also which direction. So let's look at scientific notation to standard form. So you'll have your decimal, and it doesn't matter how many decimal place values here. You'll always see it multiplied by base 10, and then you're gonna have an exponent for your base 10, so something right here, okay? So the exponent, if this exponent is positive, that's gonna tell us to move the decimal to the right. So that'll be important for us. Positive exponents, move the decimal to the right in our decimal part of the scientific notation. The number will tell us how many times to move that decimal. So if the exponent is negative, then we'll move the decimal to the left. And again, the number tells us how many times to move the decimal to the left. So that's pretty much all we need to remember for scientific notation. But if that doesn't make sense because this is new, let's look at some examples. So like this one, right? Let's change this into standard form. It's just a regular number. So I'm going to take my 3.18 here. I'm just rewriting my decimal. And then I look at my base 10s, right? Because base 10, that's how our number system works. But I see I've got an exponent of 7, which is good. This exponent of 7, I can see that it's positive, first of all, which tells me that I'm going to move this decimal to the right. Okay, but again, how far to the right are we going to move this? Well, it's a 7, so we're going to move it 7 place values to the right. So I go to my decimal, 3.18, and I move the decimal 7 place values to the right. 1, there's 2. Now you can see that as I move to the right here, there'll be some empty place values. We'll explain that, but let's move it 7 times first. So there's 1, 2, 3, 4, 5, 6, and 7. So this is where the decimal will end up. And then all these empty place values, really if you look at that decimal in scientific notation, there's just a bunch of zeros there. So we don't show those zeros, okay, because it terminates. So that means we can just fill in any empty place values with zeros as well. Okay, so our new number, let's rewrite this, but without all the moving the decimal stuff. 318, and then I count 1, 2, 3, 4, 5 zeros. Now you can put the decimal there if you'd like. It's not really going to change the value, just so you can remember that it's there. And yet some students like to put the commas there so that we know the periods. So the original scientific notation, 3.18 times 10 to the power of 7, really represents the number 31,800,000. And that's as far as we need to go there. So this example will work very, very much the same. All right, so yeah, we did change that exponent to a 5. But again, the process is going to stay the same. Let's look at just the decimal portion of the scientific notation. 8.793. And we're going to move the decimal, but it's based on our base 10 exponent. So let's look at the exponent there. It's positive 5. So this means we're going to move the decimal to the right. But how far to the right? And again, we're moving it to the right because it's positive 5. If it were negative, we'd move it to the left. But since it's a 5, we're going to move it to the right, 5 place values. Okay, so now that we know that, let's go back to the number, 8.793, and move this decimal 5 place values to the right. So there's 1, 2, 3, and again, we got some empty place values. There's 4, there's 5. That's where the decimal will end up at. And I'll just fill in these blanks with zeros. So let's write this again, but again, without having to show this decimal moving. So 879,300. If you like the decimal there, show it, but you don't have to, and then throw in some commas if you'd like to see the period. So this ends up being 879,300, and again, that's it. That's the number. This number could be shown in its regular form like we see, or you could write it in scientific notation. Why would you show it in scientific notation? I don't really know. Most scientific people that I know don't actually use scientific notation, unless again they're dealing with extraordinarily large or small numbers. So on this example, we can see now that the exponent's negative. That's going to be important for us. But first, let's write that decimal, 1.27. In fact, you know what? I'm going to write it over here, 1.27. Why am I putting it on the right instead of the left? It's because it's a negative exponent. And this negative exponent, well, that tells me that I need to move the decimal to the left. So we're going to move the decimal to the left. Again, it's left because it's negative, and it's a 3. So we're going to move it to the left 3 place values. Okay, so let's move that decimal 3 place values to the left. There's 1, then 2, then 3. So this is where the decimal ends. And so I'm going to go back and just any empty place values, just fill in with zeros. So what's the number we end up with? Decimal 00127. Now for me, this from what I understand, this works in Canvas, but I like to see the 0 in front. That would work too. That's more of a just Mr. Sells and nerd thing, so you don't have to put the 0 there in the front in the ones place value, but I like to see it there. So if you like to see it there, put it. If you don't, then don't. It's still the same value. But that's our final value as a decimal. But you'll notice as well, if you take scientific notation, on the last 2 examples we did, the exponent was positive, and we get usually pretty large numbers. This time the exponent was negative and it gave us a decimal value. That'll be important for us when we start changing standard form numbers into scientific notation. So here's this one, and again, let's change this into a regular number, but you guys try this one out. Take 30 seconds, see if you can do this one, then we'll go over it. So let's go and write just the decimal part of this for now. So 1.234. Now again, I'm putting this on the right because I see my exponent for base 10 is negative, which means I'm going to have to move that decimal to the left. So I'm just giving myself some space over here to work with. But again, it's important to notice the 8 here is negative. So we do know we're moving the decimal to the left. That's the first thing we should notice. And then we see the 8, so we'll move it 8 place values to the left. All right, so let's get started there. We see where the decimal is. We'll move it 8 place values to the left. There's 1, 2, 3, 4, 5, 6, 7, and then finally 8. So this is where the decimal will end up. And again, I'm just going to fill in any empty place values with zeros. 1, 2, 3, 4, 5, 6, 7. And like I said, I like to see that 0 in the front. So for me, I guess that's 8. Well, let's go and write this then without the decimal moving there. So I like to see that 0 in front. We got 1, 2, 3, 4, 5, 6, 7 zeros, and then 1, 2, 3, 4, 5. So again, this is a very small number. It doesn't matter that it's very small. And remember, the negative exponent is not going to make this negative. It just means it's a very small number, that's all. Which it is, it's a very small number. But that's as far as we need to go on this one. So let's talk about changing standard form, just a regular number, to scientific notation, which is okay, you can do that. So we need to remember what scientific notation is. Remember, you can only have one number, one digit in the ones place value, and it just can't be 0, that's it. It doesn't matter what comes after that. We know that we'll see multiplied by base 10 with some exponent, okay? So the first thing we'll do is we'll determine where the decimal is in the regular number. Then we'll determine where the decimal needs to be, which is, again, it'll be between the first non-zero number and the next number. It doesn't matter what that second number is, though. Okay, so we just need to determine, again, we'll find the decimal, we'll put the decimal where it will need to go in scientific notation. Then we can figure out the number of the exponent in base 10 just by determining how many times the decimal moved. Now that doesn't mean we care right then if it's positive or negative. We'll determine that later, which is these last two steps, a couple of conditional statements. If you look at the original number and it's less than 1, I guess that's the second one there. If it's less than 1, then you know you have a negative exponent. Okay, so that's again, like the last two examples where we saw decimal value, 0 point something, it's less than 1. But if it's bigger than 1, then we know that the exponent will be positive, okay? Now, that may be kind of confusing since this is so new, so let's look at some examples, see if we can clarify this. So here we have the number 190. Let's take a closer look here. So 190, some students say, well, there is no decimal, because that's the first thing we should do, identify where the decimal is. Okay, just because we can't see it doesn't mean it's there. Remember, the decimal is always to the right of the ones place value. So there's 0 in the ones place value. I know there should be a decimal right here, okay? Well, in scientific notation, where does the decimal go? It goes to the right of the first non-zero number to the left. And so I got a 1. The decimal would have to go to the right of 1. So this is where it will be, okay? So this means that in my scientific notation, I'd have 1.90. It'll always be multiplied by base 10. I just have to figure out the exponent. So I can see that the decimal moved, and again, I don't care about direction. You could count from the purple decimal or the red decimal. I'll start with the red. It moves 1, 2 times. So I know the exponent is 2. The question is the 2 positive or negative? That's the last thing we need to figure out. Well, the original number there was 190. And last time I checked, 190, it's bigger than 1. Okay. Bigger than 1. So that tells us that the exponent is positive. Now, you don't have to put a positive sign here. You just keep it as 2, which means it's positive. And this is formal scientific notation to represent 190. So this number, yeah, it's pretty big, but it's no problem because we just need to figure out what the decimal will look like. So we know that there is a decimal there just to the right of the ones place value. It needs to go between the first non-zero number to the left, that's the 2, and it looks like it'll be between the 2 and 6, okay? So we know where the decimal will need to be. That's going to make that decimal 2.69102785. And it looks like we got 1, 2, 3, 4, 5 zeros. Now, when you're writing your decimal out, if you have any zeros on the tail end of the number, as it turns out, you can just make those phantom zeros because it means the decimal terminates anyways. So I'll keep it like this just to make the number smaller. But if you want to keep the zeros there, I believe that's okay too. Now, we know that the decimal is always multiplied by base 10. We just got to figure out what that exponent is, right? So how many times we move that decimal? So I'll start with the red. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. So we know the exponent is 13. But again, the original number, what was that? 26,910,278,500,000. That number, it was definitely bigger than 1. So since it's bigger than 1, we know the exponent is positive. Okay, so we'll just keep it like that. And that right there is our scientific notation. You know, again, if you put the 5 zeros there, that's fine. Technically, you can put as many zeros there as you want. Just, again, are they significant or not really depends. And with the number as large as 26 trillion like this, some students may even, or people may say that this 5 right here is not significant, and you can go down the line, depending on what you consider significant or what you're doing with this number. All right, so here we're going to start with the decimal value. We'll change it into scientific notation, no problem. So we see where the decimal is right now. We know where it needs to be. It has to be between the 1 and 2 because in the ones place value, we need a non-zero number. Okay, so it can't go here and it can't go there. Right? Otherwise, there'd be zeros in the ones place value. So we end up with this decimal, 1.23. And the decimal is always multiplied by base 10. We just got to figure out what the exponent is. So how many times was the decimal moved? 1, 2, 3 times. So it's an exponent of 3. But our original number, this one, was smaller than 1. Less than 1. So this tells us that the exponent will be negative. So that's all I got to do. The last thing I got to do here, make the exponent negative. That's it. Scientific notation. All right, so kind of a small number, pretty small number here. Let's go ahead and change that into scientific notation. Now we can see the decimal again. Way over here on the left, we know that it needs to go just to the right of the first non-zero number, which the first one I see is 4 on the left. So the decimal goes on the right, which gives me the new decimal, 4.57689. So there's our decimal part of the scientific notation. It'll be always multiplied by base 10. So let's go ahead and figure out the number of the exponent for base 10. So how many times did this decimal move? 1, 2, 3, 4, 5, 6 times. So it's a 10 to the power of 6. But is the 6 positive or negative? Well, the original number is very small. We can see a 0 in the ones place value, which tells us this is less than 1. So again, that tells us the exponent will be negative. Okay, so that's 6. We know it's a 6, but it's a negative 6 in the end. Again, we found our scientific notation. Now there's our two objectives again. I can write any number, big or small, in scientific notation. We did start with the second objective, though. I can change scientific notation into regular number. So as long as you guys feel comfortable with this, the assignment should go pretty quick.